Thank you. And can everyone hear me in the back there? Certainly sounds loud up here. I don't know. It's been a tremendous experience already for me just today being here at the Linda Hall Library. As far as I can tell, this is a unique resource in the world, a private research library devoted to science. And I got to go downstairs and look at the stacks and the older journals and go through the rare books exhibit and everything. And so it's a wonderful privilege to be in the vicinity of this place, and I'm very happy to see that they're having public talks, especially on such an interesting topic as extraterrestrial life and aliens and other things that I'm going to have very little to say about. So I wanted to start my own talk with a confession. I hate it when speakers start by apologizing, but nevertheless I'm going to do it because the thing I'm going to be talking about is time travel, the idea especially of traveling backwards in time. And clearly this is related to traveling faster than the speed of light. And clearly both ideas are related to extraterrestrials with arbitrarily advanced technology. What would they be able to do? Could they actually warp space and time so much as to travel backwards in time, travel faster than the speed of light, visit us, have visited us in the past? But what I'm going to do is set the stage. I'm really going to talk about the physics of time travel, what it would mean, is it possible, what do we know and we don't know, and in fact there's a lot that we don't know. It's kind of embarrassing that we don't know more than we do. But then I'm going to leave it up to you to decide what the aliens could do with that knowledge and what they're going to learn that we don't know. The first thing to emphasize is, of course, that the idea of time is a fascinating one in and of itself. It takes us from our everyday lives. We move through time. You all knew that to be here, you had to be here at 7 o'clock. You knew what that meant. You knew what to do with it. But it's a mystery. We don't know how time works at a fundamental level. And to quantify this, the researchers at the Oxford English Dictionary found that time was the most used noun in the English language. Now, these days, we don't care what dictionaries say. We care what the internet says. So I checked. On the internet, I looked at various words that you might think are popular. Space, much less popular than time. Money, much less popular than space, which is that's encouraging. Fun, love, sex. Peace versus war, really not very optimistic there in terms of the number of pages found. Harry Potter, small but catching up. And time with almost 1 trillion web pages that mention the word time in there. So I don't even know how that is possible, that there are literally 1 trillion, right? This would be, 1 billion, literally 1 billion web pages. One web page for every 6 human beings here on Earth that talk about the notion of time. So clearly we're interested in it. We're especially interested in the notion of going backwards in time travel. And we get a lot of our feelings for what time travel is from fiction, from movies and TV shows, books and so forth. It's a fascinating subject. We approach it from all different ways, traveling through space, hopping into boxes of one form or another, aging backwards in time. Here's Bill and Ted, who had excellent adventures with historical figures. Clearly, this is something that fascinates us for some reason. So let's just start by asking, why is it so interesting to contemplate going backwards in time? What is it that makes it something we like to think about and to dramatize in movies and books and so forth? And the simple answer is that time travel seems paradoxical to us. It seems, without thinking about it too hard, but a little bit, that if you can travel backwards in time, bad things can happen. So the picture has the time-traveling cat about to sneak up on himself. That would be bad. We often dramatize it even a little bit more by saying, well, what if you traveled backwards in time and you killed your parents before they met? Then how did you get born? Because they couldn't give birth to you. And that is a legitimate puzzle. Of course, it starts by asking, if we could travel backwards in time, what would happen? And so the simple answer is, well, you can't travel backwards in time. Any questions? I have more to say than that. So it turns out that you can do better. It's true that the simple ideas that you might have about time travel would lead to some paradoxes, but you have to decide, does that truly mean that time travel is simply logically impossible? Or is there some way around it? Could we possibly do better? Well, you can do a little bit better, and this seems like a cop-out, but the basic rule that has to be obeyed is that there are no paradoxes. What this means is that even if You could travel into the past. What you could not do is change it. And I really want to emphasize this, that as far as we know, even if it were possible to go back into the past, nothing that you could do once you got there could affect the series of events that we know happened. So as characters from TV show Lost say, whatever happened, happened. If you can travel back into the past, you can't mess with it because we know it already happened. It's different from the future. We think that for the future, we can make choices. You can decide today what to have for dinner tomorrow night. We think that that's something that you're allowed to do. We do not think that you can decide today what to have had for dinner last night. Okay? We believe there's a fundamental asymmetry, a difference between the past and the future. The past is settled, the past happened, it's set in stone, but the future is up for grabs. Time travel gets in the way of this way of thinking about the difference between the past and the future, and that's really what's at the heart of why it bugs us, why it offers fertile ground for fiction and for movies and so forth. If time travel were possible, it would necessarily imply a form of predestination. What you were able to do in your own personal future is limited if that personal future happens in the past. If there's something that you know happened, like you were born, and you say, okay, let me imagine that I can travel into the past. Let me imagine that I can hop in a time machine and go back to a moment before my parents left. What would stop me from killing them or somehow stopping them from meeting? And the answer is something. You might not know what, but it's just like having a prophecy. It's just like Harry Potter knowing that either he or Voldemort is going to have to die. We don't know how it's going to happen, but it's going to happen. Even if you can go backwards to visit your parents before they left, maybe that is possible. What's not possible is that you can prevent them from having you, because we know that already happened. Now, the basic reason why this annoys us is because we think we have free will. We think that if we did hop into a time machine and travel to the past, and there we were with our parents, we could then be free to make the choice to prevent them from getting together, killing them or something less dramatic than that, but somehow changing what happened. The point is that what we think of as free will, I hate to tell you this, is really just kind of an approximation. At the level of the deep down laws of physics, for the most part, the laws of physics don't have free will in them. If you know what something is doing, if you know what a box of gas is doing, or a pendulum, or a planet moving around the sun, and you know the laws of physics, you can predict what it will do in the future. The reason we think we have free will is because we don't have that information about ourselves. We don't know that much about the universe. We know some crude things, but we certainly don't know what we're thinking, much less what our friends are thinking, much less what other people in the world are thinking or what other things are going on in the world. So there's a tremendous amount of freedom open to us when we contemplate what could happen in the future, just because even if it is determined, there's nothing that we can do about it. That doesn't help us any. A lot of people are disturbed by the idea of determinism, the idea that if we have the system of the universe right now perfectly, we could predict the future. I'm here to tell you, don't be disturbed. The idea of determinism is not like an ancient, wise man who says, this is what will happen in the future and there's nothing you can do about it. It's not like that. The idea of determinism is an annoying little kid who says, I know what you're going to do next. And you say, well, what am I going to do? And the kid says, I can't tell you that. And then you do it, and the kid says, I knew you were going to do that. That's what determinism is in the real world. The universe knows what you're going to do, but you don't know, and it's not going to tell you. You do know what happened in the past. There's an asymmetry between the past and the future because the early universe was a very, very special state. I can recommend a good book to read about this if you're more interested. But the difference between the past and the future comes down to this idea of entropy. The early universe was low entropy, which means it was orderly, it was neatly, precisely arranged. There was a boundary condition. We know what the early universe was like. The future is completely unconstrained, as far as we know. We don't know what the future is like. So given what the universe is today and the past boundary condition, we can more or less figure out what the past was like, whereas we can't figure out what the future is like. That's why we think we have free will toward the past, but not the future. You see, what the problem is that if you have time travel, if you can go from here into the future and then loop around back into the past, then there's no clean distinction between the past and the future. This idea that we know the past, but the future is up for grabs, gets destroyed if you can travel into the past. If you could do that, then your personal future would be part of the universe's past. And there's no way to say which is the end that is determined, which is the end that we're able to affect in any way. So the point is that you could imagine consistent histories in which you travel to the past, but they're very, very highly constrained. Knowing that your parents gave birth to you, if you can go visit them in the past, is like knowing what is going to happen to you next year. It's not knowledge you're normally thinking of as something you have access to, but that's what time travel does. So again, the simple answer would be time travel is impossible, but we're going to think about it a little bit more carefully. So there's one big aside, one big caveat to all of that, which is that I'm speaking the language right now of classical mechanics, of mechanics as Isaac Newton would have understood it. But we know better. Classical mechanics is not how the world works. There's something called quantum mechanics. And quantum mechanics plays with our ideas of determinism. We can't predict the future exactly. Probabilities become involved. And there's a very good reason for thinking that when you observe something in quantum mechanics, you can have a particle that is spread out. There's no location for it. There's different probabilities of observing it in different places. But when you look at it, the universe splits into multiple copies. A copy where you saw it here, a copy where you saw it there, a copy where you saw it there. In other words, quantum mechanics seems to imply that there are multiple copies of our universe. And that, at least logically, opens the possibility for going backwards in time and messing with the past. Namely, you can mess with a different version of the past than the version you actually grew up in. So here's my one slide about quantum mechanics. Quantum mechanics implies that there really could be multiple worlds, like season 6 of Lost. There's multiple timelines, okay, where different things happen. They branch out. They're equal to some point, and then some different event happens in the two worlds, and they go their different ways. If this is true, we can imagine this is one version of the universe with time going bottom to top. This is another version of the universe, time going from bottom to top. And these universes are identical up to this point. What happens in universe number 1 is that your parents meet, they give birth to you, you grow up, you're a very disturbed child, but you're an eccentric genius, and you build a time machine. And you use your time machine to travel backwards in time, and then you take out your anxieties by killing your parents. But you do it in a different version of the universe. And then you continue to exist in that version of the universe. You're older, you're orphaned now, you're a little bit less embittered or more embittered, depending on how that worked out for you. But your parents are dead and they don't give birth to you in that universe. Now, this is logically possible. It has been suggested by this guy, David Deutsch, who is a very respected Oxford physicist. He's trying to point out, as theoretical physicists like to do, that these things might be conceivable to us. But nobody has an actual plan for making this happen. No one has a scheme for starting in one universe and going to the past of a different universe. And if you did, let me point out, this universe still exists. You're not in it anymore, you moved, you changed addresses, but this whole history still happens. So your parents still met, you were still born, your parents are still alive there. I think it's a cold comfort to think that you can change a version of the past if the version of the past with which you are familiar is still there. You can't change that, again, because we know it happened. There are never any paradoxes. If you invent a scenario in time travel which involves paradoxes, you're not playing by the rules. So, what are these rules about which we're talking? And now we can get into some serious thinking about physics. So this man, Isaac Newton, so today, for the first time in my life, I got to leaf through a first edition of Newton's masterwork, because it's here in the rare books section of the Linda Hall Library, of the Principia Mathematica. Newton was the one who set out all of the major, well, not all of, but the major advances in both science and math that enabled our understanding of the clockwork universe. The analogy was suggested to me that Newton coming up with his theory of classical mechanics out of the blue, almost like that, would be as if the Wright brothers had gone to Kitty Hawk and built a 747. You would have thought that what Newton did would have taken hundreds of years to get right, but he did it over a couple years when there was a plague in England and he had to leave Cambridge and sit and he got hit by the apple, and you've heard that story. So here is the setup that Newton proposed, and even though there's a lot of diagrams that are intimidating to us when we're taking physics classes and so forth, the basic idea is actually pretty intuitive and it makes sense to us. There is space, there's the space around us, there's the arena in which things happen. Space is full of locations where there are different objects. Some locations are empty, some are occupied. And there is time. So what happens in Newton's universe is that space exists, it's full of stuff, and space happens over and over again. And the stuff in the universe changes a little bit from place to place, from moment to moment, and time is the label on different moments of the universe. Time is what prevents everything from happening at once, as someone once said. So time is the ordering. The universe is like a film strip in this way of thinking. It's like a sheet of film and there's different frames, except that there's an infinite number of frames, and every frame is a different moment in the history of the universe. And this division of the universe into space and time is absolute. It's there, everyone agrees on it, you can measure it, nothing mysterious about it. So, given that setup, you can ask, can you travel through time in a Newtonian universe? And the simple, jokey answer is yes. If you sit around here for 24 hours, you will travel into tomorrow. You always travel through time. You always move through the Newtonian universe at 1 second per second, or 1 minute per minute. Everyone does the same thing. That's the secret to Newton's universe, is that everyone moves forward in time, 1 second per second, and everyone agrees on what that means. Everyone knows what a second is. You can build clocks, you can measure time, and you can agree on how much time has elapsed between one event and another. That's what it means for space and time to be absolute in our Newtonian universe. You can always change your perception of how time feels. You can go into suspended animation, for example. You can just go to sleep, and time seems to go a little bit faster. You can have a cup of coffee, or you can be tired, and your perception of time changes, and that's because your body, is full of clocks. A clock is just something that does the same thing over and over again in a predictable way. Your heartbeat is a clock. Your pulse, your breathing, the cycles of your central nervous system. And the problem is that they're not very good clocks. A clock should be accurate and predictable. Our bodies are affected by all sorts of things, by going to lectures that sort of send you to sleep and all things like that. So your perception of the passage of time might be sloppy and imprecise, but time itself, according to Newton, is absolutely rigid. It's absolutely doing the same thing for every reliable clock. So there's a way of thinking about this Newtonian universe that Newton himself didn't think, but we're allowed to think of it, which is to say, take the whole shebang, all of space and all of time, and call it space-time. You're allowed to do that. No one is stopping you from doing that. If you want to locate something in the universe, an event in the universe, you need to tell me where it is in space and when it is in time. To come to this lecture, you had to say it's at the Linda Hall Library at 7 p.m. You had to give both of those pieces of information. So we can think of them all together as one four-dimensional space-time. Space itself is three-dimensional. There's up, down, left, right, forward, backward. There's no other perpendicular directions in space, but there's also the direction of time. So we can think about this as a collection of events in this four-dimensional space-time. There's no reason to think of it that way because space and time act differently, according to Newton, but you can think of it that way. The question then is, how do you divide up space-time into space versus time? And whenever you're asked a question like that, you should think of it operationally. In other words, you should think about, what is the experiment I would do? What is the apparatus that I would build to actually make this happen? Don't think of the whole universe with things happening very far away at different moments of time. Think about things you could build and what they would do. So Newton says, if you're here and you know that what time it is right now, you want to ask the question, what is happening far away, but at the same moment of time? What does that mean? What that means is you build two clocks, you synchronize them so they're agreeing with each other, and then you send one clock far away, and then it just sits there, and you have a bunch of clocks, and you can do this throughout the universe. Even though it's an engineering problem, you have infinite resources. So you set up a clock at every point in space, and you make them agree, they're synchronized, and that tells you what it means to have two different moments, two different points in space, but at the same time, simultaneously in the universe. So you need good clocks, ones that remain synchronized, ones that flow at the same rate. Then along comes this guy, Albert Einstein, in 1905, to say, actually, you can't do that. And you're always shown pictures of Einstein when he was in his dotage. He let himself go a little bit. The hair was going back, and he was wearing sweaters. But when he was a young guy inventing these theories of space and time, someone was combing his hair, and someone was dressing him very, very nicely. So Einstein says the following thing. He invents a new theory of space-time called special relativity. And he says, actually, you can't do that process that you need to do in the Newtonian universe in order to tell you what it means by the phrase equal times at different points in space. And the reason why is because when you start a clock moving through the universe, suddenly it goes out of synchronization. And this is not a problem with your clock. This is not some failure on your part to build an accurate clock. This is a deep fact about the world, that if you have a clock and you have two clocks that start the same and are synchronized, and they're both very well built, one stays stationary, but the other one goes on a journey and comes back. When the one that comes back is compared to the one that stayed behind, they will not agree anymore. That is just a true statement about the universe. We can do experiments. We've put clocks in airplanes and sent them around the world and compared them to ones that remain behind, and they're different. This is a true fact that you have to learn to deal with. What this means is that this absolute time of Isaac Newton isn't right. Time is individual. Time depends on the trajectory that you take through the universe. It's not a feature of the universe once and for all. It's a feature of your path through the universe, and different paths can experience different amounts of time. Now, this seems very different than our everyday experience, but let me try to convince you it's not quite as crazy as it sounds. The motto of relativity is that time is like space. So what does that mean? Well, here is space, okay? That's just a tabletop, some flat surface. And you all know that if I draw 2 points on a tabletop, I can certainly create different paths that connect those points such that the paths have different lengths, different distances. There can be a straight line path, that's going to be the shortest distance between those 2 points, but there can also be curvy paths. Every curvy path will have a longer distance than the short path. So what Einstein says is that time is like that. Time is just like space. The elapsed time that is read on your wristwatch as you go through the universe is analogous to the elapsed distance that you travel as measured by an odometer if you're walking down the street. It will be different to different people who take different paths. There is one huge and important distinction, which is that in space, the shortest distance between 2 points is always a straight line. In time, the straight line corresponds to the longest possible time. So what that means is that if you're sitting here and you have your watch and you're saying how long it is, someone else starts next to you, synchronized, and flies away, and then comes back. They go on some curvy path through space-time. When they come back, they will be younger than you. They will have experienced less time. They will not have felt anything funny about it. To them, time was passing at 1 second per second. That's what time does. But your second is not the same as their second because you're traveling on different paths through space-time. So if you start with a rocket ship, the point is that to make any of this real, you need to go close to the speed of light. And you don't go close to the speed of light in your everyday lives. You don't experience this. So when we talk about it, we don't normally talk about fast cars or running as fast as you can. We talk about spaceships. So if you have a spaceship here with two different little probes, and it sends out these probes on different paths, so the probe accelerates outward and then it comes back close to the speed of light, they can all have clocks that are initially synchronized, but compared to the spaceship that just moves in an uninterrupted path, the one that accelerates a little bit will experience a little bit less time. The one that accelerates a lot will experience a lot less time. So if you want, Einstein is giving you a different way to travel into the future. It's still true that you will travel into the future 1 second per second, but because your second isn't the same as everyone else's, you can choose to reach the future faster, if that makes sense. If everyone else stays behind, you can zip out close to the speed of light, come back. You've experienced a week passing. The rest of the world has experienced 100 years. What you can't do is go back. Okay? According to Einstein, there are still limits on what can happen, and that limit is expressed by the ultimate speed limit on the universe. This is the speed of light. And I have to introduce one technical term that is extremely helpful for the rest of the talk, and that's the idea of a light cone in space-time. So I'm going to try to explain to you what this means. Here is, I'm, as you know, not only a scientist, but a highly accomplished artist. So here is my sketch of you, and you have a light bulb. And what you do is you flick the light bulb on and off very quickly. So what happens is the light bulb emits light in every direction, and those little rays of light travel outward from the light bulb in every direction at the speed of light. So here is this circle represents at some moment in time, very soon after you flick the light bulb on and off, how far has the light gotten? Where has it traveled to? So the light is traveling out in every direction in space at an equal speed, and that's going to keep happening. And Einstein's speed limit says that you can never catch up to the light once it's past you. You can never move fast enough to reach the speed of light or even go any faster. So the light keeps moving away from you. You can run as fast as you want. You can hop in the space shuttle or in a DeLorean or whatever you want. You will never be able to catch up to that beam, that sphere of light spreading away from you. So what that means is there are places in the universe, in the four-dimensional space-time universe, there are events that you can never reach. So if someone says there's a great party next Friday night, but it's on Alpha Centauri, okay? It's 4 light years away. It takes at least 4 years to travel at the speed of light to get there if you travel at the speed of light, but the party is next week. That party is inaccessible to you by the laws of physics. You cannot get there because you cannot travel fast enough. And if we were to portray this state of affairs on a space-time picture, so now we have again space and time. Here we are, we let the light bulb go, and what happens is that the light from the light bulb travels outward and gets a bigger and bigger circle at every moment of time, so the whole thing describes this cone. And that is the light cone. And Einstein's rule is that starting from any point, I can draw a light cone into the future, and everything that I can possibly do must be inside my light cone. There are events out here, parties I would love to go to, but to travel to them, I would have to move faster than the speed of light. Those points are outside my light cone. I can never get there. I can get to Alpha Centauri 4 light years away, but I cannot get to Alpha Centauri next week. That is inaccessible to me. So this idea that there's a light cone and you have to stay inside the light cone no matter what you do, is what replaces Isaac Newton's idea of space and time as absolute things. What Einstein says is that these divisions, these slices here, time as opposed to space, erase them. They're not there. They're not really part of the universe. What Einstein would say is, I wish I'd drawn this, but what Einstein would say is that this light cone is real. That's part of the fabric of reality. These slices of the universe into time versus space are just fictions. They would not be agreed upon by observers who were moving at different speeds. So here is Einstein's version of space-time. There's no slices, there's just light cones. So you could start with different clocks, and they have to travel inside their light cones. And the point is that you wouldn't notice any difference between Einstein's view of the world and Newton's view of the world if everything was moving much, much slower than the speed of light. That is our everyday experience. That's why we think that time is absolute. That's why we think it makes sense to talk about an event happening very, very far away at the same time. But this division of slices is absolutely arbitrary. According to Einstein, what really exists are light cones. Okay, that was a little bit of a digression to understand what Einstein said about how you can move through space and time, but it has nothing, it in no way has changed our conclusion, which is that you still need to move forward in time. You need to move toward the future. In Newton's version, you have to move toward the future because space and time are absolute. You just have no choice. In Einstein's view of the world, you still have to move toward the future. In fact, you're a little bit more constrained. Not only do you have to move to the future, but you have to stay inside these light cones at every moment. So if you want to travel backwards in time, this story of Einstein's is of no help to you. You can travel to the future faster by moving close to the speed of light and then coming back, but if you want to go to the past, you're still stuck. However, this is Einstein's special theory of relativity. He invented it in 1905. He then spent the next 10 years thinking about how to reconcile this idea with gravity. And he eventually, in 1915, published the general theory of relativity, which says something remarkable. It says that space-time can be curved. Space-time is not a rigid structure that is there once and for all. Space-time has its own life. It responds to stuff in the universe. It responds to matter and energy, and we can bend it and warp it. That when a beam of light gets deflected by some massive object, it's not because that massive object is really pulling out with some force. It's because that massive object is bending the fabric of space and time around it. So when the Earth moves around the sun, it's not because the sun is pulling on us with a gravitational field, says Einstein. It's because the sun is warping the space-time around it. The Earth is just trying its best to move in a straight line. But there are no straight lines because space-time itself is curved. So we end up orbiting the sun. That's how gravity works. Gravity is the bending of space and time. It has its own geometry. And this has dramatic effects, not only for theoretical physicists, but for the real world. Because this is really time as well as space that is getting bent, what this means is that the amount of time that will elapse, that you will feel on your wristwatch, depends on the gravitational field that you're in. I already told you it depends on how fast you move through the universe, but it's also true that how much gravity you feel affects the rate of time. Roughly speaking, time moves more slowly in a strong gravitational field than in a weak gravitational field. And this is relevant to technology. This is the global positioning system, the GPS system that you use to not get lost when you're traveling through a strange town. You ask your car, where is this party that I want to go to on Alpha Centauri, and it gives you directions. So the way that GPS works is that there's a set of satellites orbiting the Earth, and you, in your car, have a GPS receiver that beams signals back and forth to the satellites, and what they do is they compare clocks. Your receiver has a clock, the satellites have clocks, and they're comparing the amount of time that passes, that it takes light, the radio signal, to get from your receiver to the satellite. So guess what? It's crucially important to understand the rate at which time is moving to you here on Earth and to these satellites in orbit. But those satellites are in a different gravitational field. Their clocks are moving a bit faster than they would if it weren't for this general relativistic effect. And that turns out to be measurable. If you didn't know about general relativity, if you didn't know that the rate of time at which these clocks was ticking was affected by gravity, then within minutes, you would be miles off in your GPS estimate. You need to know what this effect is to get right where you are in the city. So it works. It's experimentally verified. Now, it's also, I have to admit, fun for theoretical physicists. We can imagine bending space and time quite a bit more. You've heard of black holes. Black holes, you've been told, are places where something that is really heavy and massive has collapsed to such a tiny region of space that the gravitational field is so strong that light itself cannot escape. And that's all correct, but I want to really emphasize how fundamental it is. What's really going on in a black hole is that there's so much gravity that the light cones have tilted, that you've warped space and time so much that this movement of light around you is being sucked into the black hole. But remember, Einstein's rule is that you need to stay inside your light cone as you move to the future. So a black hole works like this. This is the singularity. This is the point of infinite density where everything is collapsed together. This cylinder is the black hole itself. And what happens is if you're out here, you have your light cone, you're not bothered, you can orbit around the black hole, you could take observations of it, whatever you want to do. But as you move closer and closer to the black hole, your light cone gets tilted by the force of gravity. And the definition of the black hole is that the black hole is the place where the light cones have tilted so much that in order to go from inside the black hole to outside the black hole, you would have to go faster than light. You would have to move outside your light cone, and that's something you can't do. So the point is that this singularity is not a place in space. The singularity is your future. The singularity is a moment in time. When you're here, you're just going to the future. You're not going left or right. You could just not do anything at all. But you will inevitably age into the singularity. The reason why black holes are so dramatic is that hitting that singularity, that point of infinite density and space-time curvature, is as inevitable as hitting tomorrow. You can't take evasive maneuvers and prevent yourself from hitting tomorrow. It's going to happen. Inside the black hole, everything crashes into the singularity. That's an effect of general relativity. However, we can now, with all of that background material at our disposal, get back to our topic. So what about time travel? I said that if you just believed in Newton's view of the universe with absolute space and time, there's no way to travel backwards in time. It's an inevitable march forward. In special relativity, there's no absolute notion of simultaneity. There are light cones, but it's still true. You inevitably march forward. In general relativity, the light cones start tilting. They're affected by gravity. So a brand new possibility opens up. We can at least imagine a gravitational field that is so dramatically strong and so twisted, literally, that the light cones form a circle in space-time. Remember, there's no slicing of the universe into moments of time. There's only at every point a light cone that tells you where you can go into the future. So if the geometry of space-time were like this, here you are, you say, I need to go into the future, so I'll go into the future. And I'm still going into the future. I'm just inside my light cone, I'm going into the future, going into the future, going into the future, going into the future, and there I meet my past self, about ready to begin on that journey. So all I did was to move into the future. I aged. And yet, when I left here, when I entered that loop, that time loop, as I got on there, I saw an older version of myself. Remember, whatever happened, happened. So if at this point I go around and I meet myself, then when I entered, my older self was there meeting me. Okay? I'm sure you all understand that perfectly. But think it through. At this point in space-time, either there was one copy of me or two copies of me or three copies of me. There's not different versions of this event over and over again. There's one event, the beginning of this journey. So if I'm going to meet myself in the past, then my past self met my future self. So general relativity, the idea that space and time are curved, opens the possibility to an honest-to-goodness time machine. If we can warp space and time so much, then we can actually travel on perfectly respectable paths through the universe, just aging into the future, that nevertheless bring us into contact with our past selves. So here is the setup. just so you can get it right. If you're Newton, you have to go forward in time. If you're special relativity, you have to go forward in time because you have to stay inside your light cones, and all the light cones are stuck. If you're general relativity, the light cones can tilt, and we can at least contemplate a warping of space-time that is so severe that you can visit a past version of yourself. So this has very vivid lessons for J.J. Abrams or Steven Spielberg or someone whoever is making the next great science fiction movies. Time travel is just like space travel. Time travel is not you hop in your sled or your phone booth and you dematerialize in a puff of smoke and you appear at some other moment of time. That's crazy talk. What it would really be like is you hop in a rocket ship, you hop in some vehicle, you travel on the right path through the universe that takes you to a sufficiently strong gravitational field that you can be flung backward in time. At no time do you disappear, you do not teleport. It's not that your consciousness is suddenly imported into a past version of yourself. It's that you get in the seat and you push the rocket in the right direction. So the Starship Enterprise is at least plausible as a time machine. It's a rocket. It can go someplace, and if the gravitational field is arranged in the right way, it could visit the past. A DeLorean that aims in the right direction and dematerializes in a puff of smoke? No, that is not the way it would actually work. Indeed, Back to the Future is probably like the worst movie in the world in terms of getting time travel right, okay? Different movies have different standards. Back to the Future is the worst because Michael J. Fox actually does things in the past that instantaneously change things in the future. People disappear from photographs and things like that. What is that even supposed to mean, instantaneously changing things when you're in the past and things? I don't know what that means, but that's okay. Made a lot of money. DeLorean nevertheless went out of business. So what we want to know is, can we warp space-time that much? Einstein, by allowing space and time to be flexible and dynamical, has opened the door. He said, here's a way we can at least imagine building a time machine. So very few people took up the challenge, but in the late 80s, early 90s, attempts were actually made to do this. How could you actually do it? You need to bend space-time so much that you could travel on what physicists call a closed time-like curve, a path through space-time that at every moment moves into the future, but globally the future gets mixed up with the past. And so here are two ideas for doing this. One is from Richard Gott, and one is from Kip Thorne, my colleague at Caltech. This, by the way, every time you see a photograph of Richard Gott talking about time machines, he'll be wearing this jacket. And that's because early on, after he was working on time machines, he gave a talk, and Robert Kirshner, another astronomer, was in the audience and said, Richard, where do you get that jacket? It must be from the future. That color doesn't exist in the present day. So he always wears it now as a tribute. So Gott's idea was based on something called cosmic strings. It was a very hypothetical idea. Remember, what we're doing here is we're not engineers, okay? We know better than that. What we're asking is, do the laws of physics allow us to imagine a scenario in which a time machine could be constructed, in which we could bend space and time so much that we could visit the past? So we are allowed to invent things that don't actually exist as long as they're not ruled out by the laws of physics. So cosmic strings are hypothetical ideas. They're basically leftover relics from the Big Bang. They're like little fractures in space-time, little tubes of energy that could be formed as the universe cools down from its earliest moments. And in the 1980s and 1990s, it was very popular to imagine the cosmic strings were relevant, were the explanation for the formation of galaxies that we see in the universe. That idea is less popular now, but the idea of a cosmic string is still perfectly respectable. And these little tubes of energy can really pack a wallop. They can really have an incredibly strong gravitational field. That's one piece of good news. The other piece of good news is that the equations that you need to solve to understand what is the gravitational field of a cosmic string turn out to be really, really simple compared to the gravitational field of a planet, for example. So Richard Gott sat down and did it. He said, what happens if I have two cosmic strings, infinitely long, perfectly straight, and absolutely parallel to each other, that are moving past each other very, very fast? Slower than the speed of light, but still very, very fast. And this was a sufficiently simple situation that he could solve all the equations exactly. It's not realistic. You can't do it. You can't build it in your lab. But it doesn't violate the laws of physics, and you can understand exactly what goes on in this situation. And what goes on, indeed, is that there are closed time-like curves. There are paths you can take around, by looping around those cosmic strings, that you actually get thrown into the past if you do it in the right way. That's the good news, and there was a lot of excitement about this. There's a little picture of Richard Gott in Newsweek holding up two strings and a little space shuttle going around them. There's also bad news. The bad news is, well, what if you don't get lucky enough to find two cosmic strings doing this? Could you imagine finding slowly moving cosmic strings and accelerating them, putting little rocket engines on them and pushing them fast enough to get to the right speed? The point is that if these strings are moving slowly with respect to each other, you don't get a time machine. You need to have two cosmic strings moving really fast compared to each other. So what if you had two slowly moving ones and you put little rocket engines on them and you accelerated them? What would happen? Would you build a time machine? No. Actually, what would happen is that putting the rocket engines on them and accelerating them, these strings, to this tremendous velocity, puts so much energy in such a small region of space that the whole thing collapses and makes a black hole. It's almost as if nature is saying, no, you should not have tried to do that. This is a no-no. You're trying to go backward in time. I know what you're doing. I'm going to stop you by making a black hole. So it's not definitive. It's one attempt that didn't quite work. Here's another attempt. This is by Kip Thorne, who's a colleague of mine at Caltech, and actually, I'm not joshing you here, is collaborating with Steven Spielberg on a movie, on a feature film based on his ideas about time travel. He was also an inspiration behind Carl Sagan's novel Contact, which was made into a very successful movie. And what Kip imagines is that there are wormholes. A wormhole is just a particularly dramatic bending of space and time that creates a shortcut through the universe. So this is an artist's impression, it's not a photograph, but here's space, and here's a little tube that cuts through it. And it's very hard to really represent accurately in a picture what a wormhole would be like, because in these curved non-Euclidean geometries, you can't draw them faithfully. The point is that this external region, what looks like this piece of paper that is bent, is actually just supposed to be the universe. This is supposed to be space as we normally observe it. There's no weird bendings or anything like that in it. But there's one little hole in space that is connected to another little hole that, from the point of view of someone outside, is really far away. But from the point of view of someone who goes through the wormhole, it's really short. So it's as if you want to travel from Kansas City to St. Louis, and you built a tunnel underground that could get you there in 5 miles. Okay, you can't actually do that because space-time is not warped that much, but general relativity gives you the freedom to imagine doing that, to building a tunnel through space that can connect two very distant regions with a shortcut that is actually very easy to get through. Now, wormholes are even more unlikely to exist in the real world than cosmic strings are. Compared to wormholes, I should say, cosmic strings are sort of everyday and mundane. Okay? Wormholes are truly exotic. We honestly don't know if it's even allowed by the laws of physics to have a wormhole in the real world. It's not just that we don't know how to build them, it's that when we try to build them, we find that we need exotic things like negative energies to keep the wormhole mouth from just collapsing and, guess what, making a black hole. That's what these things tend to do. But we're being open-minded. We're saying, let's imagine for the moment that we can, number one, find a wormhole. Number two, keep it open. Okay, so the wormhole is a tunnel that we're supporting. It's not going to collapse. But the way to think about it is really just some sphere, some region of space that I would go into and I would pop out somewhere else very, very quickly. So I have two very distant objects, and I can move them around. So what Kip Thorne was able to show is that, imagine these are the two ends of the wormhole, okay? So these are the two mouths. So I haven't drawn the wormhole itself, that's invisible, but you imagine you hop into this sphere and you pop out the other one instantaneously, okay? And I put two clocks next to them. They both are synchronized, and you can sort of guess what's going to happen. I keep this wormhole throat, this mouth of this wormhole here, stationary. It just ages directly upward in time. Whereas this wormhole, I put on a rocket and I move it out very fast, close to the speed of light, and then I move it back. By what we already talked about in special relativity, this wormhole mouth that moves close to the speed of light and then back experiences less time. So this clock goes from reading 12 o'clock to 12:10, while this clock goes from reading 12 o'clock to 1 o'clock. But here's the secret. When you pass through the wormhole, you do it instantaneously. So you do it at the same time according to these clocks. In other words, if I go in here, I come out there at 12 o'clock. If I come in here at 12:10, I go out there. So I'm not only traveling through space quicker than I should be allowed to, I'm traveling through time quicker than I should be allowed to, and I can go backwards. I can travel into here, and I would pop out there. And then I could move around and visit myself in the past. In other words, if you give me wormholes, which I know is a lot to grant that I'm allowed to build these in my secret scientist laboratory, but if I could do that, and you let me move them around, I could build a time machine where one was not there to begin with. That's the good news. The bad news is that outside the wormhole, there's energy that flows, and you can't help that. That's quantum mechanics. There's always a little bit of energy. You can't really pin things down absolutely perfectly. There are quantum fluctuations. And what happens is, as you're trying to turn this into a time machine, the energy that is flowing in between the two wormholes grows and grows and grows until it becomes so large that everything collapses into a black hole. This is not a theorem, this is not absolutely rigorously established, but this seems to be the lesson of a lot of smart people who've thought about this problem very hard. So, unfortunately, it's kind of embarrassing. I can't tell you the answer to the question, in general relativity, can we build a time machine? I can tell you, number one, that we know how to try, and number two, that when we do try, it never seems to work. Everything collapses into a black hole. That's the best we can do in the current state of the art. So it seems to be a hint that some people take, some people choose to ignore. I mean, there's a lot of money to be made in ignoring the hint that everyone else pays attention to if you can really be clever enough to find a way around it. But the bottom line, as I see it, is that it's easy to imagine building a time machine in general relativity, but when you try, you run into trouble. We can't prove that you can do it. We can't give you an example that we know works. We also can't prove that you can't do it. I would bet, given even money odds, that the ultimate laws of nature say no. You cannot build a time machine. You cannot travel back into the past. Everything is well behaved. That's really why you can't kill your parents. But I can't prove it right now. I'm not absolutely sure. We need to work harder to understand what actually goes on in the real world. So the take-home message, three of them. One is that even if time travel is possible, paradoxes are not. Paradoxes are not problems with physics, they're problems with logic. If something happened, then it happened. You can try to wriggle out of it by invoking quantum mechanics or something like that, but if there's some place in the multiverse where something really happened, then in that place, in the multiverse, that thing really did happen. The second thing is that traveling through time is like traveling through space, both in the relatively down-to-earth sense, that by taking different paths through the universe, I can experience different amounts of time, and in the more advanced sense that I can curve time, just like I can curve space and imagine looping backwards on myself. Therefore, in general relativity, according to Einstein's theory of space and time, I can conceive of building a time machine. It would not be puffs of smoke. There would not be flashing lights. I would get into a rocket ship, I would go off in the right trajectory, and I would come back. However, it doesn't seem to work according to current theoretical technology. Every time we try to do it, we run into some problem or another. Now, physicists are very bad at predicting what they'll be able to come up with in the future, so I'm hoping that if this is wrong, a physicist from the future comes in and tells me about it right now. Thank you. Now I think we're going to take questions.
We have time for a few questions. We have 2 microphones. I have one. There'll be one in the back too. Just please raise your hand.
It's my understanding at the time of the Big Bang, just for, nanoseconds, non-mass entities went faster than the speed of light. And I was thinking somewhere down the line, probably past my lifetime, would it be possible to distort ourselves into something without mass and then transport ourselves somewhere else without affecting anything and then reorganizing?
Right. I know what you mean, but I don't think that that's the right way to think about it. I think that I know what you've heard, and the problem is that physicists often get this a little bit mixed up when they try to explain it to people. I think the right way to think about it is that nothing travels faster than the speed of light. Not material things, non-material things, your feelings, your thoughts, quantum mechanical wave functions. Nothing ever travels faster than the speed of light. There are ways of describing what happens in the universe where you use language as if things are traveling faster than the speed of light. For example, as the universe expands, 2 points far away from each other can be spoken of as if they have a velocity with respect to each other. We talk about distant galaxies receding at a certain speed. And Hubble's law, the law of the expansion of the universe, says that the velocity of a distant galaxy is proportional to its distance. So the further away a galaxy is, the faster it's moving away from us. So you don't even need the early universe, the first nanosecond after the Big Bang. Right now, if you go far enough away, there's some galaxy that is moving away from us faster than the speed of light. But nothing is moving faster than the speed of light. So how do I reconcile those 2 statements? The point is that that's not really a velocity. What Einstein really says is that you have to stay inside your light cone. And what that means is that no 2 objects can pass by each other faster than the speed of light. This idea that a distant object is moving faster than the speed of light is just a fiction. It's a convenient way of talking about things. And what's really happening is the amount of space in between us and that galaxy is growing as the universe expands. But therefore, we will never be able to use this phenomenon to actually cheat, get around the light cones, and actually get ourselves somewhere far away faster than the speed of light. The microphone disappeared.
Hello, I'm right here.
Right here does not help me, okay. Yes.
Okay, early on you said that a lot of if you were getting closer to the speed of light, then certain things would behave differently. But isn't speed relative to a particular point? So if I measure myself, the speed of myself relative to an atom going through the Hadron Collider, am I not approaching the speed of light? And why don't those laws apply?
Yeah, no, that's absolutely true. So I hope I didn't say what you said that I said. If you travel close to the speed of light, as far as you're concerned, everything is absolutely normal. You never see your watch doing anything funny. You don't feel time passing slower or faster or anything like that. You're just in a rocket ship. You're having a good time. Time is moving forward at 1 second per second. The differences in the amount of elapsed time are only discernible when you then compare yourself to the person who didn't go in the rocket ship, to the person who stayed behind. So indeed, it's all relative. That is the point. One journey was accelerated, the other journey was not accelerated. Therefore, they feel different amounts of time having passed.
Also no. Hi. So what I understood from this is that you can't really travel to the past, but you can travel with that theory of the cone. You can travel to your past present. So like when you go around, you can go around too far that you go before you started the journey, but only to the point where you started the journey. Is that what you're trying to say?
Well, that's certainly true. So even if all this is possible, there is a moment when you start to travel on this loop through time. So if you're young here and then you get a little bit older, you can, when you travel back, you meet yourself at the point where you began that loop through time. And if that loop through time didn't exist back here, then you can't ever visit there. Another way of saying it is, Stephen Hawking made the joke that we know that time travel is impossible because we have not been visited by tourists from the future. Okay?